But if someone were to come along and like push us down into our seats, that would be more than 1g that we would be experiencing. So here I have some example. All right, and g forces, of course, are in all different directions as well. So g forces, you're always experiencing that 1g as you walk around. That's a vertical force that's pushing you down towards the earth. But the g forces, can be to the side, up, down, as it was playing that roller coaster. That's kind of the fun of it. Like you're going in all different directions. So here we have a Porsche 918 Spyder, and it can go from 0 to 97 kilometers per hour in 2.5 seconds. I pulled this off from the internet. Hopefully it is right, but it will go pretty fast. I did kilometers per hour here on purpose, just because I like for us to use some different units from time to time, because that is going to be important for us to note. So this graph gives the speed f of t in kilometers per hour of the car after t seconds. So one thing I did on this graph that you'll see done on a lot of problems sometimes, notice that my axes are not labeled. And then it gives you this sentence right here. It says the graph above gives the speed f of t in kilometers per hour of the car after t seconds. So f of t is labeled right here on our y-axis. T is labeled on our x-axis here. So what is t measured in? Seconds. So we're going to label this here seconds. And then f of t, what is f of t measured in? Kilometers per hour. Okay. So we are supposed to estimate the car's speed after 2 seconds. So 2 seconds is right here, and here's our graph. We are supposed to estimate that speed. Who can give me their estimates there? Okay, about 90. Now, Bo did that really quickly. He didn't do any tangent lines or find any slopes. Why did he not have to do that? This is the graph of our speed, right? Well, the graphs that we were looking at before were not the graphs of our speed. They were the graph of our distance that we had traveled. So if we looked at the graph back here, if I want to know here at 50 seconds, if I want to know speed, I needed to look at slope, because I needed to look at distance divided by time, right? If I just go right here and look, the only thing this distance tells me is that I've been like about 2,700 feet, right? It tells you how far you've gone. So it's really important what you have on those axes. Here, this gives us the speed, 90 kilometers per hour. We don't have to do anything except for read over here that it's around 90. Maybe a little more, but about 90. So, at what time on the interval from 0 to 2.5 is the car traveling at the highest speed? What's the answer to that? What? 2.5? All right, why is that? Okay, very good. Now, again, like my mind will say it's not steep there, so it's not going fast. But that's not true, right? Because we're looking at a different graph. This is speed. So wherever that graph is the highest, that's where our speed is going to be the highest, even though it's not steep at that point. Now, our graph is much steeper like over here. But that does not give us speed, right? That's something different when we're looking at the steepness of the graph that we're going to talk about in a second. So it would be at 2.5 seconds there. So now, this time we want to estimate the car's acceleration after 2 seconds. Now, acceleration is the rate at which our speed is changing. So, and this is going to be a little bit tricky because of units here. So, whenever we talk about acceleration, the units that we typically are going to use are going to be something like feet per second, or miles per hour. In this case, we're doing kilometers, so kilometers per hour. Now, we do have a problem here. Our problem here is this. I've got kilometers per hour here, but I have seconds on this axis right here. So, I'm going to have a hard time finding acceleration where I don't have those units to match. I guess I could report this in kilometers per hour per second. You could use those units, but that's not very standard. You're not going to see that given very often. So, here in this case, we want to know acceleration, which is actually the slope of this graph. So we're going to do like we did on the other. And we're going to draw in a tangent line as best we can. So we're going to draw in a line here that just barely touches that graph. And so I'm going to pick me a couple points here for this. I'm going to use this point right here, which would be 0.670, and we'll use this point right here, which is 290. And we can find the slope between those points. So we would say 90 minus 70 over 2 minus 0.6. So we get 20 over 1.4. Now, for our units here, this is kilometers per hour, and this is seconds. So I would really rather have kilometers per hour. That would be more helpful for me. So what I'm going to do is I'm just going to convert that 1.4 seconds to hours. How can I do that? We'll divide by 3,600 this time. So if we do that 1.4, let me get my calculator. So that I'm not going to be doing in my head. So 1.4 divided by 3,600 is going to get, so we're doing 20 kilometers per hour over 0.0038, no, there's an extra zero there, hours. So if I do 20 divided by, if on this calculator, that could possibly be rounded off, because usually I think it keeps 6 decimal places, and after that it rounds. So if you do second and the negative button on these, it takes the answer from the line before. So second and the negative here will take the answer from the line before. So that will give us, and you can see I think that was rounded a little bit because it looks like it was 0.00038 repeating was the actual decimal for that whenever it writes this crazy stuff right here. So that will just give you a little bit more accuracy. So we get 51428.6 kilometers per hour. Now, I really need to convert that to meters per second, which is not easy. Wonder if Google will do it for me. I bet it will. It usually will. Let's see. Let's see. Kilometers per hour equals this many meters per second per second. I was wanting a type-in box. It'll make me think about it. All right, so if I take this and multiply it by, let's say it's 5 decimal places. 1, 2, 3, 4, 7, 7, 1, 6, 3, 4, 9, 3, 8. Okay, I get 3.96825. So 3.96825 meters per second per second. Now, what was a G? 9.8. So this is a little less than half a G, right? That you're feeling at this particular point. Now, that is the G that like throws you back in your seat whenever you take off. So that you would probably feel some at this case. But is acceleration the highest at this point right here? Because acceleration is the slope of this curve in this case. Where is acceleration going to be the highest? At the beginning, right? So somewhere here in this beginning, and if you've ever ridden in a fast car, particularly my experience I think of is riding with Connor's mom here when she had that black car. And that thing was crazy fast. I don't know if the new one's nearly as fast. Is it nearly as fast? No. It was crazy. Like, way different than a gas motor, too. Like, way different than a gas motor. Because it would just, like, it was like a rocket. It was just, like, instant fastness. And it would really throw you back in your seat. But if you've ever ridden a fast car, it throws you back in your seat at the beginning. But then you're still going to feel a little bit of it, but it's not accelerating as quickly here. Top end is not going to be accelerating as quickly as it is at the beginning. So we would say here at the beginning. So we're going to estimate how many G-forces the driver will experience at the highest acceleration. So we're talking about, I would probably use this little segment right here, tangent line somewhere in here. I'd probably use this little segment. So obviously this is 0, 0. That makes it easy to figure. And then here we've got 0.2 and 20. So if we do our slope formula here, we're going to have 20 minus 0 over 0.2 minus 0. So we get 20 over 0.2. Remember, this is kilometers per hour, and this is still seconds in the bottom. So if we want kilometers per hour, we're going to take that 0.2 and divide it by 3,600. So it's 20 kilometers per hour over 0.0000056 hours. And we get 3600. This is kilometers per hour. Now I like to write my units like this, kilometers per hour. I find kids mess it up less if it's written like this. It is possible to write it this way, kilometers per hour squared. What I find kids do wrong a lot, if you write it that way, is they put the square on the wrong part. They do kilometers squared per hour. Kilometers squared is an area per hour, which makes no sense in this case, right? So both of these would be okay, though. And then we need to use that conversion factor here to do meters per second. So if I take this number and multiply it by this conversion factor, which I'm not going to make you do this on your own, so don't worry too much about that. We can get bogged down in it's something good to know, but we can get bogged down in it. So we got 27.7778. So 27.7778 meters per second. And if we take that 27 and we divide it by a G, how much was a G? 9.8. So if we divide it by 9.8, we're looking at 2.83. Or about 2.83 Gs. Which seems a reasonable estimate to me. They said yesterday in that video that most roller coasters are designed somewhere between -2 and +4 Gs here. So certainly the feeling you get whenever you're thrown back in a seat in a car is not going to be like an incredible amount of G-forces, but it's going to be significant. If you guys have watched Top Gun lately, G-forces are a big deal. Connor's going to be Top Gun, probably. Good chance of it anyway. So if you are, you need to come back and give us a talk on the G-forces whenever we do that. So I think that's all kind of interesting. This is all something like to consider in design of all kinds of things, right? Because you don't want to, especially with roller coasters, you don't want to make a roller coaster where everybody's blacking out on it, right? Nobody's going to want to ride it. There'll be some crazies that want to ride it, but you're not going to have a long line if half the people on the roller coaster black out every time. And you're probably going to have a lawsuit somewhere. My guess is if half the people that ride it every time are blacking out, there's probably going to be some actual damage to somebody eventually. So you've got to kind of balance that out there. But all very interesting things. All right, here's a totally different example that's made up and probably not all that like critically important, but it could apply to other situations. I tried to make a really generic situation that I could control. We got Mrs. Hurl is trying to get all the books returned to the library. She was in the library whenever I wrote this problem. I guess I should change that to Miss Wallace now. It is 10 days before the deadline. The number of books still missing is given below. Estimate the rate at which books were returned in books per day on day 1. So we're looking here at these things being turned back in. I doubt that Miss Wallace or Miss Hurl are like keeping charts and knowing rates and stuff like that, but there could be things on a much larger scale that you would be interested in here. In this case, perhaps like absentee voting or something like that. You probably are looking at that a little bit differently, trying to find patterns and see different things there. So we're going to estimate the rate at which books were returned in books per day, right? Notice this is measured in books. This is measured in days. So if we want to know books per day, we need to know the change in books over the change in days, which is just our slope, right? So if we're looking at day 1, day 1's not on here, but we could use day 0 and day 2 to estimate what's happening here. So we could do 75 minus 82 over 2 minus 0. We're just using those 2 points, 0, 82, and 2, 75, to find a slope. So whenever we do that, 75 minus 82 is going to give us negative 7, and 2, so we get negative 3.5. Now, let's talk about that negative here for a second. Because it says estimate the rate at which books were returned on day 1. Does it make sense to have a negative answer for that? No, that would be like books are being checked out. So we have to look at what we're given. We're getting a negative because what's reported is the books that are still missing, right? So as they are turned in, we have less books missing. But to answer this question, it doesn't make sense to have that 3.5 there because there are fewer books missing, which is why our rate is negative. But the books returned would be positive. So we would, in this case, report 3.5 books per day. So you just kind of have to read into the situation to see what. Now there are times where it would be appropriate to use the negative. For example, if it said estimate the rate at which the number of books missing is changing, then you would say that that rate is either a negative 3.5 or that it's decreasing by 3.5 books per day. All right, so you guys do the same for 7. Estimate the rate at which books were returned in books per day on day 7. Now, the best we can do here is to just use 5 and 8, although 7 is a little closer to 8 than it is to 5, so it's not a perfect estimate here, and if we had more information, that would be helpful. So if we use 5 and 52 and 8 and 30 to estimate that, we're going to get negative 7.3 repeating books per day. And this might be actually something, yes? Your best bet is to pick the points that are closest to the day that you are looking at, right? So it would be, like if we use 3 and 8, that would give us an estimate, but if because this is asking for that instantaneous, like on day 7, what's the rate? So we want to know right at 7, which we can't find. So the closer you can get to day 7, the better the estimate you're going to get. Yes. Yeah, if they had asked you for day 6 or day 7, you'd get the same estimate. Yes. No, you won't divide it. So it's over this time period from day 5 to day 8, you've got about 7.3 books per day that are coming in. So 5, 6, 7, 8, all of those days have that average time. So it might actually be that, obviously, you don't have 7.3 books coming in every day because you can't well, I don't know. Some kids might turn in about a third of a book once they're done with it, but they're going to have a fine for that. So, but you're not going to have parts of a book coming in. I'll let y'all see Margaret Freeman's calculus book from last year. It only counted for about a third of a book. Luna got a hold of it. It was sad. I didn't make any of you guys use that one. I had extras, but you're gonna see that on all of those days. So this is still an estimate. What we're really given, that 7.3, is the average rate for days 5 through 8, but it's as close as we can get to that instantaneous. Now, if we had more information, if we had an equation for this, then we could give the exact rate at that point. But obviously, we don't have that at this point. Eventually, we'll get to the point where we'll have equations for some stuff. And some things like books being turned in, you are never going to have a perfect equation for. That's where modeling comes in, where we make equations to look like our data, even though it's probably not going to be exactly like our data. And this might be something you're interested in because you can see the rate that the books are coming in at first is slow, but days 5 through 8, it really picks up faster. So if you're studying like trends of what's happening here, you might need to, like, obviously this is a really simplified example, but let's say we're looking at like votes coming into to a center that's counting like absentee ballot sort of votes. So you might, if you have studied these patterns, you might see people typically tend to turn in more stuff on these days. We should have more people staffed on these days. They're not going to turn it in at the beginning because everybody's procrastinating, right? It's going to be the rush at the end, and then, or maybe not so many people. So you could use it for planning purposes if it were on a much larger scale. If it's just at the Elkin High School Library, probably unnecessary, but I needed to make an example that was manageable for me to deal with. Plus, I don't like making up examples about voting situations and just throwing numbers out there that might be totally inaccurate, because I don't want you to think that I actually know those things. So I use more simple things. But there's lots of places this could come in play. Okay, questions? All right, so I have a